So, today I'd like to tell you about the sense of touch, and then we'll cover the sense of taste and the sense of smell as well, because they're all related. So, to start, I'd like perhaps someone could come and do a simple sort of touch problem of picking things out of a bag and recognize them before looking at them. Yeah? Okay.
Oh, I think so. You want me to describe what it is?
Yes.
It's a squishy ball, probably maybe like a stress ball.
Okay.
Do you want me to take that?
Yeah. So
Oh, the eyeball!
how did you know that it was squishy?
I squished it.
Okay. And then, so what told you that it was squishy? How do you determine squishiness?
I applied pressure and it conformed to my hand when I applied pressure.
Okay, so you sort of felt your hand move.
Yeah.
Good. So knowing how much your hand is moving is important for determining squishiness. Okay, next one.
Okay, oh, we have a smaller ball. It's harder. Oh, it's like rubbery. It's like harder. It's not as squishy. It has an indent. Bouncy ball?
Possibly. Okay.
Can I take it out? Oh, bouncy ball!
You could throw it if you want. We'll get it back. Okay, next.
Oh, we have a cube, small cube with indentations of different indentations on each face. So I think it's a die. It's a die. Cool.
Next. We're down to coins.
Oh no. We have a pencil eraser.
Ah, okay. How do you know that?
Well, it feels rubbery, and then it has like a hole for when the pencil would go.
Okay, so you can feel those shapes.
And it's like one of those diamond ones, so I kind of remember what it would look like. I've seen a pencil eraser like it.
Okay, so you can see a diamond shape just with the feel of your hand.
Yeah, like I feel like triangles in different faces. Oh, okay, so we have a hard, small shape that's smooth. I think it's a shell. I can feel like the rough edge of the shell comes around. It's a little shell. Okay. I think we're at coins now. Oh, this is going to be hard. Okay, so do you want me to tell you like which coin it is?
That's right. They're the Canadian coins. So.
Okay, so there's a thin, small one, so I think it's a dime.
Okay. How did you tell it was thin?
I compared to the other ones.
And what? Well, what?
Like how much my finger could like just.
So you felt it how?
I felt it on like the edge on the side.
Okay. You put your fingers on the edge there?
Yeah, I felt like the round edge. We have a thicker, big one. And the edge is not completely round, so it's a loonie. It is a loonie. The toonie is totally round. It's serrated like
I didn't know that.
Okay, a smaller one with lots of patterns, and it's thicker, so it's a nickel. Yay!
Well, thank you very much.
Thank you.
Amazing what you can tell. Your sense seeing with your fingers, seeing shapes, seeing textures, seeing how soft things are, how hard things are. And so how do you do that? That's what we'll cover in the next hour or so. And what we have to start with is certain bunch of receptors that will go in detail later on. But you can see those are the receptors that exist in your skin. And with those receptors, you can tell edges, you can tell textures, you can even read letters if you learn to read Braille. You can even recognize faces. We didn't have any statues for you to recognize today, but you recognized the triangle of an eraser and the square of a die. And you can do that with just a few receptors. And the first one we'll consider is this one here, the Pacinian receptor. Now, how does it transform mechanical energy, which is how much pressure is being exerted, into electrical activity? Well, the first thing that happens is that you get deformation of the skin. That then, in the case of this receptor, opens up the sodium channel. And sodium flows into the cell, raising its potential. Now, if the potential here, where it's widened a bit, that's called the initial segment. If that potential reaches a certain threshold, then that cell will generate an action potential. And then if that axon is myelinated, that is covered with this insulating myelin, it'll jump from gap to gap in this myelin. And that speeds it up something like tenfold. So myelinated fibers, which are most of the fibers that we'll be considering, travel at a healthy speed. Now, the next thing is what happens to, how do you tell how hard things are being exerted, how much pressure is being exerted? Well, you have a frequency code. If you haven't reached threshold, if you're just pressing a little bit, no action potential will be generated. If you're pressing just a little bit, as you see here, then maybe one action potential is generated. If you press harder, the potential inside that initial segment gets higher, and when it gets higher, the number of action potentials increases. So frequency code is ultimately what one cue as to how much pressure is being exerted. Now, the other important thing here is that this frequency doesn't continue forever. So there's just a few action potentials, and then it becomes quiet again. And that's because here the potential inside the initial segment adapts. So it comes back down toward zero, even though pressure continues to be applied. Now, this particular fiber, the Pacinian fiber, is called a rapidly adapting fiber. The RA we'll use as to symbolize it. You will also see that there are slowly adapting fibers. So this potential will persist for some time without falling significantly. And so these action potentials will continue for a longer time. The other thing about the firing frequency versus pressure is that as the pressure rises, the action potential frequency doesn't continue rising linearly, but starts falling off. Now, you'll see in one of the problems of the problems, practice problems this week, that has a useful function. It's not there out of willy-nilly. Now, we saw that when the stimulus adapts. How does this occur and why? Well, the how is that the receptor potential adapts. You saw that. And in the case of this one, the Pacinian afferent, when you press down, this Pacinian afferent has this special onion-like configuration. These are like onion rings that surround the afferent. And when you push down, all the rings get deformed. Then gradually these inner layers stretch back to their normal shape. And as a result, this hole here becomes small again, this receptor, and the potential in here drops again to its normal level. Why does this happen? Well, let's say, for example, you put on a shirt. Well, you care about the fact you put on a shirt only the moment when you put on a shirt. During the day, you don't want to be bothered with the feel of the pressure of the shirt. Okay? So a lot of things are the same way in the somatosensory system. You only want the brain only wants to be alerted to the changes that occur. If nothing's changing, stop firing. Don't waste energy. So on the skin, this is the very surface of the skin, and this is deeper in the skin. You find all these afferent names, or these afferents with these names. Don't worry about remembering these names. I'll show you in a moment. We've got a sort of short code for them, and that's what we'll use throughout the course. What you can see here, some exist on the very surface, and some deeper in the dermis. And the other important thing is that on any part of the skin, there's only 4 receptors. So on the back of the hand here, you tend to find hair receptors. On the palm of the hand, you don't find hair receptors, you just find Meissner receptors. So you find this or this, but not both. Now, you'll see that some of these, like the Pacinian afferent, is rapidly adapted. Well, the hair and the Meissner is also rapidly adapted. So we'll call these two RAs, rapidly adapted. And the other thing we'll call is if it's on this very surface, epidermis, we'll give it the nomenclature 1. If it's deep in the skin, in the dermis, we'll give it nomenclature 2. So you see that both the surface and deep in the skin contains 2 types, a slowly adapting and a rapidly adapting. Again, rapidly adapting and slowly adapting. The size of the receptor field increases as you go deeper and deeper into the skin. So this is an example of a small receptor field from, let's say, the RA1 receptor. You can see it's very small here. And this is a large receptor field from that Pacinian afferent, the RA2. Now, recall in the case of vision, you had 3 types of cones. And as a consequence of these 3 types of cones, you were able to distinguish something like 2 million colors. Well, again, with touch receptors, you've got 4 different types. And although nobody has gone around and figured out how many millions of different touch attributes you can distinguish, it is most certainly as good as the sense of sight. So it's probably in the millions as well. And you could tell by the demonstration, the beginning of the class, how many things one could sense, how many qualities that you could sense with these five receptors. Okay. And without them, then, let's say you only had 1, the sense of touch would be far less vivid. Something like being colorblind and seeing everything in black and white. Now, in addition, there are 2 types of free endings. So rather than having some sort of structure up here. We just have the fiber ending getting smaller and smaller and smaller in these the surface of the skin. And these are sensitive to pain. And there's two types. One that is fast, again, because this one is myelinated, you can see little bumps along it. And another one that is not, and so this is slow. So you can see, as a function of time, this is when the stimulus comes. The fast one, you get a fast, slow, or a short response, and then a later, very long-lasting response. This fast one causes an early, very localized, you can tell where it's coming from, and a very intense pain. That's what this one will, when you activate this one, that's what you sense. When you activate this type of afferent, it's a later, it's poorly localized, you can't tell exactly where it's coming from, and it's from a low, it feels like a long-lasting dull pain. Now, when you press on your nerve, your hand or leg will often fall asleep due to the pressure on the nerve. And the pressure blocks action potentials in the large fibers first. So you'll first lose the sensation of touch, and only later the sensation of pain if the pressure continues for a longer time. So if you want to, you can test that. You can have your hands fall asleep and try using a little pin and prick it a little bit and see if you can feel that. You should still be able to feel the pain. Now, how pain works is thought to be controlled by something called the gate control theory, produced by Patrick Wall and Ronald Melzack. And they thought it was a balance between what large fibers are signaling and the small fibers are signaling. And if the large fibers are giving you more sensation than the small ones, then you don't feel pain. If it's the other way around, then you do sense pain. And probably for that reason, things like rubbing on some area that's sore relieves the pain. Besides pain, you also have an important clue of temperature. You have some afferents that respond to when something is cold, and other afferents that respond to something that's hot. Because of my spinal cord injury, I don't have the sense of pain or the sense of temperature. And so I have to be very careful when I take a shower in the morning not to turn the water up too high. I can feel the temperature with my arms, but if I just left it on my legs, I could burn myself. Again, these are fairly fast conducting because they're myelinated. You see the little bumps in them. They don't hold for burning or freezing stimuli because those are things that activate the pain receptors. Okay? So they're just for cold and hot, but not burning or freezing, which is way out here. Okay, let's say the brain sensed an axon firing. Okay, it's firing like that. What does it feel like? If an action potential fires, what does it feel like? Does it feel like it's smooth? Does it feel like it's some object touching you, some fine object? Just by the firing frequency, you can't tell much. Okay? You don't know exactly what's going on. It could be something small that's going repeatedly touching you, okay? Something small vibrating. let's say, a bee landing and inducing buzzing. And that would produce this rapid activation, long-lasting activation. But that's because it's being repeated over and over again. It's activating this RA receptor, rapidly adapting receptor. Again, you wouldn't know because the action potentials look the same. It could very well be something that's small, but it's pressing and denting the skin, and it's just maintaining that compression, and it's activating your slowly adapting receptors. Or it could be, again, it could be something small, but rather than being smaller, it's something big, again, vibrating, something like you're holding on to a power drill. So you don't know which of these it is, and therefore, just from the axon, you can't tell. The brain needs some other mechanism to tell what the stimulus is. And so the brain must somehow label that afferent, put a label on that afferent. Now, in the case of an internet, when you send a signal, you're one of these, and you would encode it, and that encoder gives signals that come from you, this red tag, and over here you have the decoder, and that decoder sends it to whoever it is you want to contact, and it decodes that, so that person knows it's you, or receives a signal from you. So that's one way of tagging. Our CNS doesn't use that system. It uses a system where each afferent has its own private line all the way to the cortex. Okay? So the cortex knows whether it's this fiber being activated, this fiber being activated, or that fiber being activated. So it's called a labeled line. And so it has no reason to encode and decode the signal. But what you need instead is lots of lines. So you have a thick spinal cord, lots of fibers traveling up it. So then within the cortex by experience learns what each stimulus is, the feel of each stimulus. And that, again, it takes a bit of thinking to start really appreciating that. When we take the auditory system, we'll see that each frequency is encoded not by how fast something is vibrating, but which afferent is being stimulated. So the fact that you hear a high note is because one particular type, one group of afferents is being active. When you hear a different frequency, it's another group of afferents. And so you're not hearing the frequency of that afferent, but just which one it is. So similarly here, and from that you can tell the frequency of the sound. And you think it's a high pitch, but really it's the neurons located over here that you're feeling or sensing. Well, same thing here. Yes, but as an infant grows, he learns that something here will something that activates these guys is a texture of a certain kind. Something that activates these guys is another type of touch stimulus. So as the child activates these afferents, it learns what type of surface he's touching and what will activate that afferent. So I mentioned the auditory system, place coding in the auditory system, and the fact that it's not how fast or what the frequency of the fiber is firing, but by which one it is. Okay, so what do we learn? So for example, if this one were activated, we now would, as an adult, you would feel a localized flutter. Maybe it's a little insect. Here we'd feel a fine vibration, And we use that to learn what texture, whether it's a rough sandpaper or a fine sandpaper. Here, we maybe sense how round or how thick a coin is. We see the spatial details of an object. Over here, we feel skin stretch. Okay, so we feel skin stretch on the top of the hand here, and compression at the same time on the inside of the hand. And that sensation coming from the skin tells us how far apart our fingers are. And that was useful, for example, in the case of the bag, to figure out whether that ball was spongy or hard. Okay, what the fingers are giving. We'll see that there's other sensors next week that also help us code proprioception, how close or how wide apart our fingers are. Now, so I'd like you to all activate your receptors for the sense of texture. And the way to do that is rub your fingers on whatever you're wearing. Okay? Feel the texture. Okay? And then just put your fingers on the thing that you're wearing and see how long, with the fingers stay stationary, you can still feel that quality, and start moving it. See how that changes. You know, how that your sense of, you can see how much better you can tell what the texture is while it's moving than when it's still. Okay? Because while it's moving, you're activating these RA1 receptors, the rapidly adapting receptors. And you can tell as you come across different bumps, how frequent those action potentials are, and in part, by looking at that, determine the smoothness of an object. Now, what's how does this information get to the cortex? Well, ignore the red line for the time being. The main way to get this information for the sense of touch is this dark line. And the dark line is called the dorsal column medial lemniscus system. And it goes up here. It's called, first of all, it enters the spinal cord and makes a synapse with a neuron that does something in the spinal cord. But also, that same axon separates and heads here and makes its first synapse up here in the dorsal column nucleus, DCN. It's over here about the beginning of your neck. And then it crosses at something called the medial meniscus, and therefore that's why it's named, and goes up to the thalamus. In this case, the ventral posterior thalamus. So like the sense of vision, it goes through a particular part of the thalamus devoted to that sensory modality. And then it goes up to the cortex. And over here in the cortex, you have the different body parts represented. And here, if it's something coming from the arm, it goes to where the arm is being represented. The red line is, we'll cover that in a moment, and it's the pathway not for touch, but for pain and temperature. Now, when it enters the dorsal column, the leg is low down to the spinal cord. It enters first, and it takes up the most midline representation within the dorsal column. The dorsal column is, here's a picture of the spinal cord. This is the front of the body. This is the back of the body. The dorsal means back. Okay, so this is the back of the spinal cord, and this takes up a position at the most medial part of the spinal cord. When the trunk comes in, the touch afferents from the trunk, they take up a more lateral position. And finally, when the arm comes in, it takes up an even more lateral position. So you can see here in the spinal cord the beginnings of a somatotopic representation, the body being represented. Now, I mentioned before that from here it follows this pathway to the somatosensory cortex. And then that the sense of pain goes up this different red pathway. That's called the anterolateral system. The main things that are important for this is that we saw before the dorsal column, the medial viscous system, the touch pathway, went up and made its first synapse in the dorsal column nucleus. The sense of pain instead makes its first synapse within the spinal cord itself, and then crosses at the same level to the other side, and then goes up the anterolateral pathway or system. Ends up in the same part of this, but the thalamus, and in the same part of the cerebral cortex. So you can see that these two pathways follow different routes in the spinal cord. And that's one reason my sense of touch in my legs is preserved. So this pathway, my dorsal columns are intact, but my anterolateral system has been damaged by the lack of blood in my spinal cord, and this is no longer working. And the reason it can do that is because these pathways are different. So what happens in the dorsal column nucleus? Okay. It's the first synapse that it makes on its way up. So the afferent starts here and travels all the way up to here and makes its first synapse there. Well, one possibility is that this is just a relay nucleus. Well, there's really no reason to have a relay nucleus. These action potentials can travel forever. At every one of these gaps, there's an amplifier, and the action potential is amplified. There's no lack of energy in the action potential as long as your myelin is intact. So there must be other reasons, and we'll see in the next little part of the lecture that there's three different functions that this structure performs. The first thing is convergence. You can see here many afferents, in this case 5, converging onto a single DCN neuron located here in the neck. And these afferents come from the skin in the back. And so the DCN that represents the back only needs one neuron to represent these 5. The other important thing is these 5 are far apart. So the area of skin that's covered here is large for this one neuron. So you don't need many of them to represent the back of the skin. So this is somewhat like your peripheral retina. You don't need many ganglion cells to represent it. In contrast, this is what the fingertip looks like. You can see here, each of these afferents have their own DCN. Okay, so there's one afferent for one DCN. So each one of these has only a small receptive field. And so your fingertip then can feel things with a lot of acuity. To show that, I'd like another volunteer to come up. Any more volunteers? in this case, I'll be touching your fingers with these two parts of a paper clip, and I want you to tell me if I'm touching you with 1 or 2 points.
Is that 2? Oh, it's 2.
Okay, we'll try another finger.
Okay.
Let's try your thumb. Is that better?
Okay, 2.
Okay. We'll come down in size then.
2. 1.
Okay, that was still 2, but pretty close together. Oh, let's pull this apart. Let's try it again. Okay.
2. 1.
Hopefully when you're wrong.
2. 2. 2.
2. Okay, very good. Make it a little smaller.
1.
That was 2. Okay. Let's try, so about this, I don't know if you can see it from way back there, but about this distance was where a threshold was on her finger. Now if you this.
1.
Okay, it was 1.
2.
2. You don't know?
No.
Yes.
2.
2. Good.
1.
Okay. So that was about, it's twice as big. And if you could see the back of the leg is even worse, the back of the shoulder. Okay. So that was about, it's twice as big. And if you could see the back of the leg is even worse, the back of the shoulder is even worse. So again, given that, you would figure the representation then in her DCN would follow the same pattern. You'd guess that a distortion of the map would occur, and we've done that. So that's one function of convergence. Different body parts have different sizes of representation, and that corresponds to there's correspondence of that to the acuity that those body parts have. The other thing that you see is surround inhibition, like we saw in ganglion cells. Some afferents are excited by inputs coming from the central region and inhibited by afferents that are stimulated in the surround region. So the only thing different is the circuit by which this is constructed. Here in the DCN, what we have is all these afferents from the center synapse onto the DCN neuron and have a positive connection to the DCN neuron. All these afferents coming from the surround don't come directly to this DCN neuron, but hit another one instead, and then that neuron, a nearby neuron, will, through an inhibitory neuron, inhibit this DCN. So the same mechanism will also accentuate things like two-point discrimination. Two-point discrimination is what we were doing with this paper clip. Okay, was this 2 points or 1 point? Now, experiments have shown that you have a tough time being able to tickle yourself. Why is that? Why is tickling yourself not an easy task? Well, one reason is this, that again, there's this thing called choroidal discharge, that every time you make a movement, there's a choroidal discharge that comes down. And that discharge can inhibit afferents going up. Now that's useful, for example, when you're doing things like trying to estimate how whether a ball has give or not by how far apart your fingers are. You, you, you don't want to be sensing the movement itself, just the position of your fingers and how compressed or uh, uh, or not compressed they are. So then, in summary, three things happen. You've got convergence, you've got lateral inhibition, and then quality discharge, which is gating how much sensory input based on the motor commands. All these three things are taking place in your DCN. From there, you hit the somatosensory cortex. Again, because your DCN had this distorted representation, the somatosensory cortex does as well. Okay, you can see here this distortion tells you that the fingers have a large representation, the face and the lips have a large representation as well. In contrast, you see the forearm has a much smaller representation, and this is your back, whole back. It's a tiny in comparison to how your fingers. Now, phantom limbs. Phantom limbs, for example of what a phantom limb is this patient. He had an amputation at about this level. He lost his fingers and arm all the way up his shoulder. But about a year later, the patient complained of the following, that he still could feel his hand in his cheek. How was that? Well, what scientists found was that during the course of the year, the face representation had expanded over the somatosensory cortex. So the arm representation was lost, it shrank in size, and the face expanded. But after a year, there was still a tiny remnant of the hand in the cheek. So that tells us several things, but one important thing that tells us is that there's plasticity in the somatosensory cortex that occurs even in adulthood. Another feature of the somatosensory cortex is that there's not just one map of the body, but there are several maps of the body. The somatosensory cortex is divided up into these sub-areas, area 3A, 3B, 1, and 2. Now, today we're covering 3B, 1, and 2. Next week we'll cover the afferents that come in 3A. They're the muscle and joint afferents that help you signal position and limb movement accurately. Now, 3A and 3B considered the primary somatosensory cortex, S1, which would be the equivalent of V1. These two areas would be the higher order areas, similarly to V2 and V3, similar to. Now, an interesting thing to note is that within 3B, there's a map of the fingers, and there's another map of the fingers in area 1, and one is the mirror of the other. So again, it's like the mirroring that we saw happening in V1, V2, V3. Now, area 1 then, these higher order areas, do different things, start specializing. Area 1 has mostly these RA1 receptors. And we said the RA1 receptors are important for texture, feeling what the texture of your clothes are. They're activated by rubbing and vibrations. In area 2, you recognize things like shape of objects, size and shape. It was what helped tell how big a coin is by what your positions of fingers were. So you'd be able to tell a shape. And this shape 2 was a triangular shape of the eraser. So all that type of thing is what this area excels at. And that's those SA2 fibers are very useful for doing that. The other thing that changes from this primary areas to the secondary areas is the shape of the receptive fields. In this one, there's still circular surround. They're small little things, usually on a single finger. And but as we go back into the brain, into these higher areas, what you start getting is things that are orientation sensitive, so that you feel a line of a particular orientation. And the receptive field gets larger, and frequently it encompasses more than just one finger. So you feel a line moving across these 2 fingers here. And they also become movement sensitive, so you're sensitive to movements going perhaps in a particular direction. And finally, the signal gets here in the posterior parietal cortex. And that's where you recognize, well, this is what's inside that bag of toys. This is where the identity of the object is revealed. Now, what will there's a malfunction in the animation here. But what one is supposed to see here is that this area here, when you expand it, you see again a little part of this finger area, let's say, expanded. You see again a columnar organization, the little columns being represented, like you have in V1, the different columns. So this figure is broken up into little columns. But what's different about here is that these little columns, rather than, for example, signifying things like orientation or other qualities, each of these columns is activated by a particular afferent subtype. So either the RA1 or RA2, SA1 or SA2. So this is the end of your labeled line. So this is where your labeled line is and ends. It starts with skin and ends here in these columns of area 3B. Okay, next let's do taste and then smell. In the case of taste, you see here the tongue, and different colors represent the different sensations of taste. Now the tongue is very touch and temperature and pain sensitive. It's as sensitive as is the tongue. So I use my little paper clip thing and measure the receptive fields of your tongue, or you can do this at home. Try that off your tongue or your lip. You saw from the diagram that both had a very large representation in somatosensory cortex. So you could tell that this would have a high sensitivity. Besides doing all that, you're also doing chemical analysis of whatever is on your tongue. It gets dissolved in your saliva. A dry tongue is useless for taste. You need the saliva to do the dissolving. Now you can see that these colors, they've got quite drawn properly, but they expand into almost everywhere. So almost everywhere feel something. But the colors tend to be stronger in different parts. So you see the back here, it's more concentrated red than over here. That tells us that the different parts of the tongue are more tuned to different tastes. The middle part of the tongue has very few tastes. Now the first thing that's activated is out here in the very front of the tongue, the ability to taste sweet or salty things. You also, on these yellow things, have the taste of something called unami. And remember what that is. That's the taste of bacon. Basically, that's a good way. It's a recently discovered taste. It used to be that we thought it was only 4 qualities, but there actually are 5. Then there's sour, and then there's bitter. So one step up from sour. Now, you can imagine that when you taste something, like you taste a sip of wine, it first hits this part of the tongue. So at first you taste how sweet it is. Then you taste how sour it is. And then you taste how bitter it is. So it has a spatial distribution, whether this, or this, but over time. So it's called a spatial temporal pattern. And we'll see the taste and smell has the same thing. You take a whiff and has a spatial temporal pattern. In both cases of taste and smell, memory is an important aspect. You have to memorize this firing over time to recognize the taste of a particular wine or the smell of a particular perfume. Now, sourness or saltiness have very simple ion channels. So there's a channel for hydrogen and there's a channel for sodium. And depending on how much is coming in, it activates those type receptors. The other taste, bitterness, sweetness, umami, have this G protein coupled receptors. So they're somewhat like the receptors in vision. They have these G proteins which produce amplification. So you need just one photon coming in, activating a sequence of things within these receptors and producing this molecular cascade and activating that particular quality. And as I said before, umami, especially sensitive to something like monosodium glutamate. So by adding lots of that tastes good. Now, each receptor you can imagine as a key, and each taste is like a key, and each receptor is like a lock. So a particular key is required to open a certain lock. A particular taste required to open up a certain receptor, and that's especially so for these more complex receptors. The ones to do with sweetness, for example, that require the G protein activation. You have many sweetness molecules, and the industry that develops artificial sweetness is trying to devise all kinds of sweetness molecules that will activate those receptors, but yet the substance itself not have any calories. Now, all over the tongue, these receptors are contained within a structure called the taste bud. The taste bud contains about 100 cells, and each cell is sensitive to a particular quality. Now, because the tongue, and we'll see later on the nose too, is exposed to all kinds of hazards. You can drink scalding hot coffee, you can have an infection, you can have toxins in your food. These cells need to be replaced. In the case of these cells, they get replaced every 2 weeks. So these basal cells down here become supporting cells out here in the walls, and then becomes taste cells over the course of 2 weeks. If these afferents are damaged, then these cells die. They don't no longer. They need some trophic factor coming from this afferent to maintain these cells. Now, where does the signal go from the tongue? Okay, here's the front of the tongue. Here's the back of the tongue. The signal from the tongue goes up different nerves, the 7th, 9th, or 10th nerve. And they have a synapse in the nucleus of the solitary tract, again distributed the same way as you see the tongue distributed. And again in the thalamus is a distribution. And finally up here in the insular cortex, insular taste cortex, again you have a rough topographic representation of the different tastes of the tongue. And the way the system works is much like the labeled line system that we saw for the sensation of touch. Now, with taste, you have something called an inborn hunger. You have this inborn desire for certain, to act for the taste, for the substances that produce certain tastes. So if anything salty, you want lots of. Anything that has proteins, you want lots of. Anything that has sugars, you want lots of. Also, at the beginning of the century, when calcium wasn't as prevalent in our diets, you find kids, young infants with lead poisoning. And that's because one source of their calcium was the plaster on the walls that contained lots of calcium. Unfortunately, the plaster on the walls was often covered with paint that had lead in it. And so there were a lot of cases of lead poisoning. Again, it's this inborn hunger for calcium that produced these incidents of lead poisoning. You also have genetic defects. You saw that when you had certain genes, genetic defects, then you were colorblind for certain colors. Well, the same thing happens here. The G proteins that are the G receptors require certain proteins to be formed, and those again can be absent, and so you can, for example, not be able to taste the bitterness in cabbage because of something different about your genes. You can also learn to dislike certain tastes. Young kids especially don't like bitter or sour tastes. Gradually we develop a liking for them over time. But kids will dislike beer or anything. That's because usually these bitterness and sourness were signaled that something's either spoiled or poisoned. But you can also teach a sort of an aversion for certain tastes. And one way of doing that is to couple it with a sensation of nausea. So if rats, if you combine a tasteless poison with a particular food, they'll learn to avoid that particular food. If you go to a restaurant and you have food poisoning because you ate a certain thing, you'll learn to develop an aversion for that particular food. But surprisingly, you won't. It's not like normal classic condition, because classic condition would give you dislike not only for the food, but also the person that you were with and the music that was being played. But this is selective just for the food. In the case of smell, This is the oldest of your tastes. And when you combine smell and taste, you have a quality called flavor. You need both to give you flavor. And as you age, especially the sensation of smell starts to get weaker, and that often produces appetite loss and weight loss. Now, the odors are produced by these tiny little molecules that you see swimming around here and entering the olfactory cell. They first have to get through this mucus that's on top of your nasal cavity. They dissolve into it like the saliva in your tongue. And you can see the different afferents have different shapes. You have something whose ends are triangular or square-like or circular-like. Each one has a different color here. And you can see that each of these afferents, each of these odor molecules, attach to these different afferents. And when this afferent then goes through the skull, this is bone here, and attaches to something called a microcell within this olfactory bulb. This is part of your cortex. Now, this is skull, and so these short afferents, if the brain inside here moves a lot, these afferents will be cut. And so if you have you get a big jar of the brain, you'll lose the sensation of smell. But luckily, like your taste cell, these smell afferents regrow and enter the cortex again and form a synapse. So after a month or so, you regain the sense of smell. Now from here, you go to several structures, one of which is this piriform cortex. And this is where the different odorants combine into the smell of certain qualities like perfume. And then from there goes the structure called the amygdala and the hippocampus. In the amygdala, you get activation of pleasant or unpleasant odors. And in the hippocampus, we'll see, is where the memories of different smells start being formed. And finally, we'll get to this part here called the oral frontal cortex after going through the thalamus. Amygdala is where you get unpleasant or pleasant, and hippocampus is the memory. In the orbital frontal cortex, you combine things. You combine smell with taste, with texture. So if you're activating, for example, eating something, it has a certain texture. Bananas have a certain smoothness. Apples have a certain crunchiness. Spices, so the pain afferents. And vision. All these modalities combine here and give you a multimodal representation of that particular food or whatever it is that you'll be eating. If you lose this area, you have trouble discriminating between tastes. Now, it takes, these afferents here are unmyelinated, so it takes time, some time to get through here. But that doesn't matter, first of all, because this is short, and secondly, because time isn't crucial. It takes a lot of time just to dissolve into this mucus. The taste of smell is not for taste of smell, time is not a crucial quality. Or a short time is a crucial quality. But the temporal pattern is, so when you take a sniff, these things dissolve and different qualities at different concentrations and dissolve rates, and so you have a temporal pattern of activating these afferents here. And again, to remember that pattern, you need memory, and memory then is an important clue for smell, and of course, different odors elicit strong memories. Is there a basic smell quality? We saw there are basic taste qualities, a limited amount of touch afferents, only 3 types of cones. But in the case of smell, there aren't some basic smells. Instead, we have something like 300 receptors. Dogs would have 3,000 receptors, many more than us. Only 3 of these 300 are drawn here: yellow ones, blue ones, and green ones. But you can imagine in reality there's something like 300 randomly distributed over the top of the nasal cavity. Now, an odor is a mixture of odorant molecules. So this is an odor, and it's made up of these individual molecules. And you'll have 3 of these types of odor molecules, 2 of these types, 3 of these types, and 1 of these types. The other thing that's important to know is that each odor, or odorant, I should say, odor molecule or odorant, can attach to more than 1 receptor. So you have a triangle part shape here, that can attach to the triangular part here. You have a square ending here, that can turn around and attach to this receptor here. Okay. Similarly, this one here has a square shape and a round shape, so this one can attach to either of these. Now, again, you can have genetic defects, so you have like color blindness. You have an inability to smell particular odors because a particular subtype of these cells receptors would have disappeared. Of these 300, you might have a few dozen of these missing, and as a consequence, be unable to smell particular odors. Now, the mapping of smell in this olfactory bulb. So each of these receptors goes to a particular position in this olfactory bulb. So you see all the green receptors, there would be, maybe a couple hundred of them across here, all would migrate to this microcell, this particular microcell, at the front of the olfactory bulb. All these types to another microcell further back in the olfactory bulb. And all these yellow ones even further back. So you see different smell qualities being represented along the olfactory bulb. Now, similar odors tend to activate neighboring microcells. So this is the sort of the representation of the nasal cavity. So what's represented on the olfactory bulb is not a representation of the nasal cavity, but instead a map of smells, not the somatotopic representation of the nasal cavity here. These green ones are sort of randomly distributed throughout here, and yet they're all congregated here at the front of the olfactory bulb. So that's the key difference between the somatotopic map and the smell map that's located there. Now again, as I mentioned before, this is a very dangerous environment to be in for little afferent. And as a consequence, these afferents are continuously being replaced over a time span, in this case, of a month. The interesting thing is that if this cell is lost, after a month it regrows, but it regrows to the same location that this original cell was represented. So this green one would grow back to this thing. If this yellow one was damaged, it'd grow back to this area. So your sense of, your representation of your odors remains constant even after it's been damaged. Just to finish up then, what we have here is the sense of smell and the sense of taste. And over here we have the limbic system. That's an old part of the cortex. And some of the structures in it are the hippocampus, the amygdala, and hypothalamus. And over here we have the neocortex, the new part of the cortex. And in the case of taste, we have got the insular taste cortex. In the case of smell, you have the orbital frontal cortex. We see that both the taste and smell has a direct input to this limbic part of the cortex. And the same thing for the taste. It's a sense of taste, a direct connection to the hypothalamus, without going through the thalamus itself. The neocortex, on the other hand, requires the signal to pass through the thalamus, as does every other sensory afferent. Okay, that's it for today.